So let us believe we have access to true mean. Alright. So when I have done, let's assume that I have done this some experiment and somehow I have got access to the true mean. Okay. So that's how we are building upon and moving ahead. Okay. Alright. So now if you have this, then how do I some examples of your velocity vectors and so on, how do I represent it? So you can say example could be ensemble mean of a velocity vector, because this xn I said is a random realization, it could be anything, it could be temperature, pressure, whatever. So if I have this, then I can say ui of xi comma t, it's three-dimensional, your velocity vector, let's say u1 in the direction of one direction of your coordinate axis is a function of x, y, z and time. So if I use over bar, that is the ensemble mean of this. So this will be in the limit n tends to infinity, your 1 over n summation n equal to 1 to n ui of xi comma t n. Okay. So note that this ensemble mean is a function of three-dimensional space and time. This is not time average. Just like the way you flip dices, each one is an independent realization. So your ensemble mean is a function of 3D space, it is x, y, z and time t. Okay, so here ui can be anything. So your ui here, ui could be u1, u2 or u3 velocity components. Okay. Alright. So now we know how to define an ensemble mean for a velocity vector, and some may have a question, then what is time average? Because in the laboratory we are continuously taking samples. Okay. So a time average can also be same as an ensemble mean, only in a special case. So we will define what is a time average first. Okay. Time average, let's call it ut, that I am averaging it in time. This is in the limit t tends to infinity, your time 1 over t integral 0 to t of your velocity vector dt. So your time average becomes ensemble average only in a special case when your mean is not changing in time, because this time average is not a function of time, it's only a function of three-dimensional space ut. Okay. For example, let's say you have two signals. Let's say there is one signal which is like varying like this. Okay, forever. So this is a number of samples, or you can call it time here, right? Or let's say, let me use the time since we have discussed this. Let's say you are collecting samples in time, and this is your temperature or any other parameter. So then the average mean will be this. This is your ut. So the mean itself is not changing in time. Such a flow, if you have a flow where mean is not changing in time, then time average can be used, and time average is same as ensemble average. But you can get many flows, like just like the engine, internal combustion engine, it is the piston is compressing and expanding, and therefore there will be an oscillatory variation in the temperature. right? So you would get a signal like this, right? So what is its mean then? The mean is not averaged over the cycle, so the mean has to be, so this red line represents the mean. So if we have this kind of a process, so this is where you have what we call a stationary flow. The mean is no longer a function of time. In this particular case, then time average can be used, which will be same as the ensemble average. Here the time is also, the mean is also a function of time. Mean is changing with time here. Okay, so therefore time average or time mean becomes your ensemble mean only in stationary flows. So it perfectly works here in this particular case, not here. So you need to do any other type of flow where your mean is changing either in a periodic sense, or it can be in a completely random sense, right? Then use ensemble mean. Ensemble mean is very generic, and therefore we will use ensemble mean as the process, okay, to continue to separate the fluctuation, because you already see a signal like this. So the question we ask is, if I have to capture this turbulence or model it, then I need to first know what are these oscillations around the mean, right? So on these oscillations in a turbulent flow around the mean is the random component or the turbulent component. I need to understand how much energy it is carrying, what it does. If I understand this, then I can model it. For that, I am removing the mean component first. That's the whole point of starting with this chapter, statistical analysis, okay? So we discussed ensemble mean and then the time mean, but we'll proceed with this ensemble mean further. So now ensemble mean itself is not enough all the time, right, to just get it. We need some higher order statistical values. So before that, let me just give you some notations that you would see in textbooks, and the notations that I will follow mostly. Okay, if I change it, of course you please let me know. So we look at some notations that we are using. Okay, so the first thing is to look at fluctuations about the mean. So if I am going to talk about mean, I mean ensemble mean. So we will not going to use arithmetic mean anymore. So mean implies true mean here. So fluctuations about the mean. So we get some notations. Notations that you see in literature. So you can usually see, let's say there is a random parameter, could be velocity, temperature, whatever, or pressure. Sometimes you will see a tilde on this, x tilde, then that is sometimes or x itself. So these are two popular in literature on textbooks. So these are the instantaneous component. Just the way you are recording the signal itself, whatever we have shown, that is oscillatory, that is can be represented as x or x tilde, and when they use x tilde, they use x for the fluctuation or x prime. This is used for fluctuation or randomness, the random component. And then we have this x, capital X, let's say, or x bar. So this is your mean or the statistical component. So in the course I am going to use this x prime and then the x bar. So when I talk, if I say u v w, that means it's instantaneous signal, and u prime v prime w prime means fluctuating velocity components, u bar v bar w bar means the true mean. So I'm going to use this notation. Okay. So now there can be signals where two signals having same mean but they have different randomness, and therefore we need higher order terms. So if I take, for example, for the fluctuations about the mean, let's say I have one signal like this, let's call it phi is your parameter, or x or v, anything. Let's say this is the signal that you have recorded, okay, n number of samples. So this will have a mean. Phi bar. So now there can be another signal. Now you get higher excursions. The mean is same. Two different signals. Let's say one is an experiment that you have done today, and tomorrow you are repeating the same experiment, and suddenly you notice that the excursions about the mean has increased. The mean is same, but somehow you see the randomness has increased. Okay, so both have same mean here. Both have same mean, and therefore we need to define not just the fluctuations about the mean, we need more than that one. So x prime or phi prime itself is not enough, so we need more than that. Okay, so both have same mean but different randomness. So now the fluctuations about the mean, we call it, let's say, x prime, right? X prime. So if I ensemble average x prime, what happens? Ensemble mean of x prime. What do I get? X prime over bar 0. Yes. If I ensemble average the fluctuating signal, okay, that means I have this random signal here, right, the oscillator signal, and then I subtract, so it's phi minus phi bar, or x minus x bar should give me x prime, and if I ensemble average that x prime, it should go to 0. If it's not going to 0, that means you are not working with ensemble mean, you are working with arithmetic mean. The average of your fluctuating signal not going to 0 means you are always working with the arithmetic mean, and that is the people said, yeah, I mean, some said, right, it's small and therefore it's acceptable to me. But we are coming to the theory here. Ensemble mean, this has to be there, and the proof is very simple here. So how is x prime defined as fluctuation? It is nothing but x minus x bar, right? Or let me write it here. So it is x minus x bar is nothing but my x prime. Instantaneous minus mean will give me the fluctuation. Okay, fluctuation, this is the instantaneous and this is the mean, 3 component. So if I am going to ensemble average, okay, so what will this be? This will be, so the ensemble average and the subtraction operation, they commute. So I can write this as x bar minus x bar over bar. Now x bar is the ensemble mean, and if I am doing another operation over it, what is ensemble mean of an ensemble mean? It's the same. Ensemble mean is not changing, that's why I call it true mean, right? So this is the true mean. Therefore it doesn't change, therefore this is 0, right? If you are not getting 0, that means you have not worked with ensemble means, you are working with some arithmetic means. Okay, so here the takeaway is, what this implies is ensemble mean of an ensemble same. It doesn't have any new changes in it, and therefore x prime over bar is 0. If it is not 0, that means this has become an arithmetic mean. And take a note here. So if x prime over bar is not 0, then you are not using true mean but arithmetic mean. So you are operating with an arithmetic mean, which is giving a non-zero value upon averaging. Okay, so as I told you in the previous graph here, so here you have same mean, phi bar is same in the two signals, but the excursions about the mean is different, and therefore we need another parameter to study, that we call variance. Okay. Let me call it x prime over bar, or simply x prime square over bar. That is in cases where two signals having same mean, I need to look into an higher order term. So is this 0? What does this imply?
X prime square and v.
So the question is, x prime square equal to 0? How do you know that?
Because every value is positive after we take a square.
What if x prime is 0?
Then it's 0, but it's
Then it's 0. Then
if all x prime is 0, then it's 0.
Yes.
Otherwise, it's not 0.
Exactly, right? So if x prime is 0, what does that mean? What kind of flow you are working with? Laminar flow. Okay, which we are not interested in this course. Correct? Okay. So is x prime, if this 0, that means yes, in laminar flows. Okay, so in turbulent flows it's not. In fact, it becomes a very important parameter to know the extent of turbulence, how strong or weak my turbulence is, right? I cannot know only from x prime. I use the variance to know how strong or weak. For example, here both have same mean here. The phi bar is same, but one may exhibit a stronger turbulence level than the other one. Okay. So we have this root mean square, right? RMS or root mean square or standard deviation. This is So sigma equal to x prime square average, and of course there is a square root of it. So square root of mean of the square of your fluctuation, RMS, root mean square. This is also often very used in turbulence literature. We look into this and we will see the physical meaning for all these things. Right now you know only about the mean and then the fluctuation component, which is x prime or u prime, v prime, p prime, whatever, pressure fluctuation, temperature fluctuations. But what is the physical meaning for the variance and what we discussed, the third order terms like this? We would need higher order terms, right? Example like x prime, x prime, x prime, or x prime fourth order terms, third order terms. Okay, so these are called skewness and flatness. But these are general statistical terms that you would see even in any finance course or general statistical course. But what is the physical meaning of this associated with turbulence, that we will see. As we go into the equations governing turbulent flows, you will see the meaning of each of these terms will pop in. Okay.